All right. Hi, everyone, and welcome to PyData Global. We're so excited to have you join us today. Feel free to use the chat feature on your right-hand side to connect with fellow attendees and share your thoughts during the session. If you have any questions, please post them in the Q&A tab, which is also on your right-hand side, and we'll address them at the end of the session. Now, it's my absolute pleasure to introduce Jacob Tomlinson and Katrina Riehl. They'll be presenting GPU development in Python 101, an exciting session we've all been looking forward to. So Katrina and Jacob, take it away, and let's give them a warm virtual welcome.
Great, thank you very much. Hi, everybody. So this is a 90-minute tutorial session that we're going to be running through. And I've got a few slides to kind of intro the session and talk things through. But like a bit of housekeeping stuff first. We're going to be talking a lot about Python code and GPUs. And if you don't have an NVIDIA GPU right in front of you that you can immediately do stuff on, that's okay. We want to make sure that you have an environment you can go and work on. So we have this platform that you can go to. It's learn.nvidia.com, and you can join this event on there. There's like a whole bunch of different courses on the like NVIDIA learning platform, and there's a code here that you should be able to see on the screen at the moment that you can put in to get access to the material for this session. So I'm just going to leave this slide up for a minute and just give folks a chance to go here. I'm also going to just see if I can put this link in the chat as well. Let's just go nvidia.com/join, and the code you need is the PyData Global DC04. Data GPUB DC04. So you should be able to go and sign up. And I'm just going to put the other link in the chat as well, just so that you've got them all. NVIDIA.com/event. Yeah, exactly. As Katrina says, make sure you do the WebSocket test just to make sure that the session stays connected and that you have access to Jupyter and everything. So I'm going to be running through in this environment. I encourage you all at this point to go and register and get set up on the platform, put the code in, mainly just because when you start the session, it's going to spin up a VM somewhere on the cloud for you that's got a GPU and pull down the software environment and get you into a Jupyter environment. But that might take a couple of minutes. And while I'm talking through the intro, we want that to be kind of chugging away for everyone. So if you have any trouble or any issues with this, I encourage you to speak in the chat. And if you have any questions about, getting set up and the course material, anything like that, please put it in the Q&A in the AirMeet kind of thing, and we can kind of chug through those. I'm hoping that I'm going to be here kind of talking and demoing and walking through notebooks, and Katrina can be kind of helping folks and answering questions in the chat there. So I'm just going to leave this up for maybe one more minute, just to give you all a chance to go and head to these places. And then we'll kind of start talking through. So, okay, we've got everything in the chat. Let's go for it. So, just to introduce myself a little bit, my name's Jacob. I work in a group at NVIDIA called Rapids. Rapids is this kind of open source ecosystem of Python tooling, basically, for doing data science. It kind of fits well into the PyData ecosystem, where we kind of add support to various different libraries, which adds GPU acceleration. Right. So if you enjoy using pandas or you enjoy using scikit-learn, we have kind of plugins for those. We have cuDF for pandas. We have cuML for scikit-learn. We have cuGraph if you like NetworkX. We have a whole bunch of other tools that let you use the GPU to accelerate various operations, but kind of access all of that through APIs that you hopefully all know and love through the PyData ecosystem. So some of these are kind of re-implementation libraries where we've just kind of mimicked the API of existing libraries, or more and more these are kind of direct integrations or direct plugins where you can just use these libraries straight away. And like the goal of this tutorial is to dig into some of this and explore how we can get started kind of in this space, assuming that we don't know don't know anything about this. So, our core goal in Rapids is to let you leverage NVIDIA GPU hardware, but without having to learn a whole bunch of new tools and change all of your practice and everything. And ideally, just reuse the existing code that you already have, but just get more power out of it, get it running faster, and therefore maybe increasing the scope of what you want to do, or try more things. So just to show you like a quick example of how our pandas integration works, we have this library called QDF. QDF comes with this plugin called qdf.pandas. And you can invoke this in a few different ways. But if you're working in like a notebook environment, or you're working in IPython, you can do this magic you can see at the top here, this load extension qdf.pandas. And so this is just telling Jupyter or IPython to load in this module into your environment. And then from that moment on, you just use pandas as you normally would. There's nothing you need to change about kind of how you're working. You just import pandas and do pandas things. But under the hood, we've got this QDF library, which is this GPU accelerated almost re-implementation of pandas. And you can use that directly if you want to. But in this situation, you can come in, you can use pandas. And every time you make a pandas call, this extension is going to intercept that call and try and run it on the GPU and leverage that GPU acceleration. But if for any reason, either it hasn't been implemented, the thing you're trying to do hasn't been implemented in QDF, or you run into some kind of error or some kind of problem where the GPU functionality doesn't work in the same way the CPU one does, the most kind of common use case is maybe you run out of memory, right? Typically on a system, your main machine has more RAM than the GPU card does itself. And so if you're loading something that's larger than the memory of the GPU, that may not work, whereas the CPU equivalent will. And in that case, this plugin will fall back to using the CPU. And so that's great. You can just run through all of your kind of standard pandas code, and it will just opportunistically use the GPU in the places where it can. And you get some great performance increases from that. And so just to show you some quick examples, operations in pandas like joins and group bys are the kind of things that the GPUs really can get stuck into. It's a very parallelizable operation. And so we get these incredible speed ups, 100 times, 150 times performance speed up just by using the GPU to do the same operation. And by using these plugins, you don't even need to change your code, right? You have the GPU, you run your pandas code, and it just goes a lot faster than it would have done otherwise. And that's it, right? We could stop the tutorial here and try and say to you all, look, there's all these plugins. Keep using the tools that you love. Keep using the PyData ecosystem. Come and install the Rapids libraries. Come and install the plugins, and you'll just get all this acceleration, and that's great. But that's not what we're here for. The goal of this tutorial is to kind of start from the bottom of what actually is GPU code. What is it like to write code for that type of hardware, and kind of work our way up the stack a little bit so that you can see all the things that you probably don't want to have to do, right? There's a whole bunch of things that you would have to learn and think about every time you want to implement something or get something done. And so coming in and using all the zero code change plugins and kind of just using your normal libraries as you would is the way to kind of be productive in this space. But by having a foundational understanding of kind of where GPUs are powerful and what they can be useful for, hopefully will build your intuition a bit of kind of when are these tools going to be useful for me, what kind of problems am I solving, etc. Now, as I said, this diagram kind of doesn't quite, I said bottom up, right? But if you look at this kind of diagram here, we often talk about this thing in Rapids and NVIDIA about these accelerated computing swim lanes. So these are kind of the levels of complexity and they're like closeness to the hardware that you can go down the software development stack. And so at the very top of this, we just have the zero code change plugins. This is where you can just use your tools exactly as you would normally use them, and they'll be GPU accelerated under the hood. And if we go one step down, these are libraries which are kind of GPU aware, libraries that have GPU backends, but you have to kind of opt in. You have to make some small changes to how that works. So this is pretty common if you've used PyTorch. You kind of you'll see the word CUDA around, and you're intentionally making tensors on the GPU and doing operations where you're being a bit more thoughtful about, I am going to use the GPU or I'm not going to use the GPU. And this is common across libraries like PyTorch and XGBoost and a whole bunch of other libraries. But then if we step kind of like another level down from that, we've got just pure GPU libraries. These are Python libraries that only use the GPU, and you can kind of come and use those when you need them. So this is cuDF, our re-implementation of pandas, QML, our re-implementation of scikit-learn, cuGraph, our re-implementation of NetworkX, or maybe directly you're going to use CuPy, right, which is a community project that matches the NumPy API. Or you're going to use Number, where you can write really kind of low-level CUDA code, but in Python. We don't have to go as far down as C++ to write code directly for the GPU. We can stay in Python world, but we can kind of get quite low level. But then we can keep going down the stack if we want to, right? We can start getting into this space of like Python wrappers for CUDA. You want to start writing some C++. You want to use some kind of maybe high-level C++ libraries for doing CUDA things, like the CCCL suite of tools, and use Thrust and Cub and these various libraries that you have on the C++ side, or you go all the way down to kind of the low-level code as well. And depending on your use case and the kind of problems you're trying to solve, maybe you want to go all the way down this stack. Maybe you're trying to build some tool or some library or some platform and you want to go all the way down. But I think if you go back 5 to 10 years, like these different layers didn't exist, right? You were kind of your only choice was to go deep down that C++ stack. But now you've got all these different choices about where you're gonna go. And so this tutorial material that we have today kind of starts at that GPU Python libraries layer, right? Where in Python space, we're going to talk about the basics of Python and GPUs and how you can write code for that. And we're going to start with some nice Hello World type examples. And then we're going to work our way up through various other libraries. Now, we originally put this material together for SciPy a few years ago. And so those tutorials are like 4 hours long. So we have quite a lot of notebooks. And I'm not going to try and rush through this in double time to try and get through all the notebooks in the session, because I think that would just, you're not going to take in the stuff. So we'll just keep working through the material that we have until the end of this session. And then, as Katrina said in the chat, you'll have access to this course on the NVIDIA Learning Platform. And you'll also have access to the VM that you can start and stop and kind of use a GPU to run through this material. You'll have that for the next 3 months. So I encourage you kind of after this session, if you're enjoying it, you can keep going and keep working through the later chapters in the material. So yeah, a little bit of an overview of what's in the tutorial. We're going to start with some real fundamentals of talking about, what is the difference between a GPU and a CPU? What is the CUDA development model? How can we just write some Python that runs on the GPU? And then we kind of dig a bit deeper into managing memory and understanding what the GPU is doing. And I kind of expect that's probably where we're going to roughly run out of time, is after getting some of these kind of CUDA Python fundamentals. And then the later chapters go on to, how do I do NumPy type things on the GPU? How do I do pandas type things? How do I do scikit-learn type things? So all of that material will be available to you after the session. So if I come out of these slides and I come over to here, just before you all join, I kind of logged in and set up here. There's a question in the chat that says, can we use Colab instead of NVIDIA's VM? Absolutely. If you go to the Accelerated Computing Hub, which is this NVIDIA GitHub repo that we have, you'll find this tutorial in here, right? GPU Python tutorial. And these are all the same notebooks that we're running through on NVIDIA's platform. But if you scroll down in the README, there is like an opening Colab link for each chapter of this. So if you prefer to be in Colab, you're more than welcome to. But I'm gonna run through this in the NVIDIA DLI platform. So I clicked start earlier, and if I click launch, it should open Jupyter up for me and drop me into here. And if I go into this folder, we've got a bunch of notebooks, and I'm gonna start chugging through these. There's a couple of, some of these are me talking, some of these are me showing some code, and then some of these are kind of labs for you to do. And we'll probably go through those reasonably quickly, given that this is a shorter session. But again, these are things you can dig into more kind of in your own time after the tutorial. But I think I'm hoping to get to the end of chapter 3 in the next, what have we got left? 75 minutes. So I'm going to open up chapter 0. I'm going to make my text a bit bigger as well. And I'm going to close that tab out. So hopefully this is big enough. If this is not big enough in the screen share, please do shout in the chat and I can tweak it a little bit there. So zero is actually the overview. I've probably said everything from the overview. So I'm going to just move on to chapter 1 directly here. So the first thing, I guess, that we're going to want to talk about is what actually is the difference between CPU hardware and GPU hardware, right? Like these are two things that I have in my machine, and I kind of, you know, when I joined NVIDIA about 5 years ago, and when I joined, I was coming in as a person working on distributed computing and cloud computing. I work a lot on Dask and other projects in the PyData space, and I came in to kind of think about this more higher level. How do all these different machines work together? And I hadn't thought about this kind of low level. And it was part of my motivation to get involved in learning some of these lower level libraries so that I could have a better understanding. And I think this is one of the first questions I had is just, you know, historically, I've bought a GPU for gaming. It's a thing I put in my machine and it makes my games look nice and go faster. But like, what does that actually mean from a computation point of view and a programming point of view? So a couple of the diagrams in here are pulled straight out of the CUDA documentation, and there's links through to those. But a lot of that documentation focuses on the C++ side of things, and so this is kind of re-explaining these things in maybe a more Python-centric way. But when we have a CPU, and I'm going to run some code on my CPU, I'm going to write a Python script. I'm going to do Python space my script on the command line, and I'm going to execute line by line. Your Python interpreter is going to run through my code, and each line is going to get converted to some Python bytecode, and then that's going to get run by the interpreter on a core of my CPU, right? And so we can see on the left-hand side we have the CPU, and we have a small number of cores, right? Somewhere between 1 and, maybe 10 or 20 cores is pretty standard to find these days in a server or a laptop or something. I know you can go bigger and get up to around the 100 core level if you get a really big server on the cloud or something. But in a laptop, it's pretty normal to have maybe 12 cores or something. And so a single threaded Python application is just going to use one of these cores and it's going to step through and leverage that hardware. Maybe use multi-processing or something and start up many processes and to leverage more of the cores, but your single application is thinking about a single threaded operation. And this CPU also has kind of these various memory caches and access to main global memory of the machine. Now on a GPU, on the right-hand side here, the architecture is very different, right? You have lots and lots of smaller cores, and each of these cores can run through kind of a single operation in one go. Now, the way that I tend to like to show this, and I'm hoping this will kind of come through on the screen share, is there's a great video, if you go on the NVIDIA YouTube channel. I doubt you'll be able to hear the sound from this. Hopefully the video is running at least a reasonable enough speed. But the guys from Mythbusters came to a conference and demonstrated the difference between a CPU and a GPU. And this is just quite a nice visual example between the two. If this is a bit choppy in the screen share, then I encourage you to just go and search Mythbusters and NVIDIA on YouTube and watch it for yourself. But they built this robot which has a paintball gun on an arm, and it is drawing the picture. It's drawing the smiley face picture by shooting one paintball at a piece of paper, one by one, over and over, right? This is your CPU. It is executing operations sequentially. And then this other machine that they built next to it, this slightly larger one, this is your GPU, right? This is a similar machine. It's a paintball gun. It's doing the same kind of thing. The intent is the same. It's going to shoot a paintball at a target in order to paint a picture. But this is a parallel processor, right? It is, in terms of construction, it's a gas tank and it's a barrel. It's just lots of barrels. And they've been set out in like a grid configuration here. And the key difference is that they've set some initial conditions. They've loaded all of these tubes with different colored paintballs, and then they can execute an operation on this paintball gun in one go. They can hit a big button, and it will just fire the paintballs all in one go, and it will paint out a nice picture in one shot. And this is kind of the difference between the two devices. Instead of executing kind of instruction by instruction, working its way through some kind of algorithm, the GPU, you set up some kind of memory condition, and then you have lots and lots of parallel threads running through, executing these kind of similar operations. I'm enjoying all the emojis in the chat, so hopefully that was a good demonstration, right? But this is kind of how we need to think about this programming model as well. And so moving beyond that, I think one of the next questions that I had initially when I was learning these things is, how do I talk to the GPU? How do I actually like tell it to do stuff? Like I know how, if I write Python code and I run that Python code, it runs on the CPU. That's just how computers work, right? How do I actually speak to this other device, this other thing in my machine? Like, what's the interface for that? And the kind of the mental model that I quite like for this is thinking about, well, what if I was going to run some code on a server in the cloud or some other, I'm going to log into some other machine and run some code somewhere else over there. I would use a bunch of different protocols and a bunch of different tools to do this. I would have my laptop in front of me, and I would need to be able to log into that remote machine. Maybe I'm going to SSH into it, or I'm going to BNC onto it, screen share, whatever it is. And then I need to copy my code to that machine. I need to probably copy my data to that machine, or that machine needs to have access to my data over a network somehow. And then I need to be able to tell that machine to run the code. And so maybe I'm going to use SCP or something, or rsync or Git or whatever it is to copy some Python code onto another machine. I'm going to SSH into it, and I'm going to run Python, my script or whatever. And this kind of model maps quite well onto the GPU. So we need some way of making code for the GPU, copying that code into memory on the GPU. We need to copy data into memory on the GPU. And then we need some method to invoke that code to start that execution. And so this is part of the CUDA ecosystem for NVIDIA GPUs. Right, so all of these different protocols that we might use for a remote server, this is what CUDA provides. And I think if you've not explored this world before, like you might just think of CUDA as like, oh, that's a C++ thing. That's like a language thing, right? But actually, like CUDA covers a whole bunch of things, and one of the things is kind of this whole interface between you and the device. So you've got this card plugged into your machine to a PCI Express connection that's connected to the CPU, and then you're going to use CUDA to do all of these operations. And so all of these high-level libraries that we've talked about, all these the CuPy, the QDF, all the plugins for pandas and scikit-learn and everything, these are going to do all of this for you. You're not going to need to worry about any of these things. You're just going to run normal Python functions, and they will handle dispatching down to the GPU. But I think we, as a 101 tutorial, we want to explore what's it actually like to write some code that's going to run on the GPU, and how do I actually invoke it, and how do I launch and run it. So I'm going to get started with the next chapter 2. As I'm going, please don't hesitate to ask questions in the chat or in the Q&A as well, because there's like a whole bunch of different concepts that I'm going to throw at you here, and different things that we're going to have to learn. And I'm sure there will be things that spring to mind. I'm more than happy to kind of take questions as we go, and it's probably useful for other attendees to hear answers to things. So yeah, don't hesitate there. But the place that we're going to start here is with a library called Number. This is a Python library that you may have heard of before, because Number's used for a few different things. It's a really great library. But at its core, the goal of Number is to compile Python code at runtime into something that can run as fast machine code, basically. And so you may have used Number before on the CPU side, where you decorate a function with the number JIT, which when you call that function, it will compile it into some fast machine code and kind of cache that function, so that every time you call that function again, you get this very optimized execution, which is really great. And we love using Number for things like that. But what you may not know is Number also has this Number CUDA subpackage, which lets you write Python code that will then be just in time compiled to code that can run on the GPU. And it also exposes all of the CUDA things that we need in order to copy the code to the machine to the device and copy memory to the device and invoke code and all that kind of thing. So for this section of the tutorial, and probably everything we're going to have time for today is going to be focused on number. And you can install number from PyPI or CondaForge or wherever. It's just a standard open source library. Now, I'm going to start introducing a bunch of different terms, and this may be term overload, and I apologize for that. But the first term that we're going to start with is a kernel. I can see a question in the chat. Let's just divert and talk about that for a second. So just to further understand the difference between CPU and GPU, can you get parallelism from a CPU by multiple cores? How does this compare with a GPU? Absolutely. So you can have multiple cores in a CPU, and your operating system is kind of handling how you're using all of those. You're probably running different applications on different cores. But on the GPU side, you're going to have many, many more cores, hundreds or thousands of cores, and you're going to kind of be using them all in concert together to do kind of a single thing. We're going to be thinking about them as a group of things that we're going to use to execute. So it's kind of at a slightly different scale, maybe that we're thinking about here. So yeah, well, what we need to write is something called a kernel. And you'll hear within the Kudu ecosystem, people talk about CUDA kernels and I've written a kernel that does this, and I'm gonna, I want to launch kernels and run kernels and whatever else. And so let's demystify this first word. In the context of all of this, a kernel or a CUDA kernel is basically a function, right? It's very similar to a function. You can think of it as the same thing. It's a block of code that I'm going to execute in a certain way. It's going to take inputs and outputs and whatever. But there are some kind of slight differences between a function and a kernel, and there's enough differences here that we have to give them a different name, basically, so that we know what we're talking about when we're describing them. So there's a couple of rules that we have when we write a kernel. Firstly, is that a kernel can't return anything, because when we run a kernel, we're going to run it maybe thousands of times in parallel on this GPU. And we don't want to be kind of collecting all these return values and figuring out where to put them. On a CPU, it's okay, like it could be allocating memory as it needs it to return from there. But if you're running thousands of times and each kernel is returning big chunks of memory, you can very quickly need a huge allocation of GPU memory for all these return values. So instead of returning anything, you must just modify memory instead. So the things that we tend to pass into a kernel is maybe a pointer or an array or an object that exists already, and then the kernel will just modify that in place. And then the other thing that we have to do when we call a kernel is that we need to specify something called a grid, right? And this is almost like us describing how many times we want to run the kernel. But we can do that in a few different ways. And there's a few kind of words here that we should introduce to talk about this. So the grid is your kind of overall computation, right? I've got a kernel that I've written, it does some operation, and I want to run it 1,000 times. That my grid size is 1,000, right? That's my kind of overall shape. But then the actual GPU hardware itself, although it's a parallel processor and it's a lot more parallel than thinking about kind of the core on your CPU, it is still a finite resource, and depending on which GPU you have and from which generation, they all have a different number of CUDA cores in them. And so the way that we handle that is this overall grid we break up into batches, basically, and we have these batches of operations that we're going to pass to the GPU. And the lower end GPUs can do a few batches, and the higher end GPUs can do lots of batches at the same time. But we break things up into this kind of standard batch size. This is what we call a block, and then we can just be streaming these blocks kind of through the GPU. Because at the end of the day, if we say my GPU has 1,000 cores or something, but I have an array with 1 million elements in it, and I want to do an element-wise operation where I do something to each element, like I don't have enough cores to do that all in one single go. I'm going to need to break this up into batches. And so we'll see these words coming up over and over of grid, the overall computation, block is like our batch size, and then thread is like a single call of our kernel. And we will need to specify all of these things as we go. But this is kind of one of the first things that we need to do when we call this function, when we call our kernel, is we need to decide, well, how big is each block going to be and how many blocks do we need? And so the number documentation is really great. It gives us some good rules of thumb for deciding these things, because ultimately the shape and size and dimensionality of your operation that you're doing on the GPU benefits from different kind of hierarchies in this space, depending on what kind of code you're doing. There's a few different kind of nuanced things, and the intent of this tutorial isn't that we get that deep into things. I don't want to spend a bunch of time talking about kind of tuning and really developing deep CUDA code, because this is a 101, and there's a bunch of great talks out there already about this kind of topic if you want to learn more. But there's a few things where, like, when all the threads in a block are running, there's a guarantee that they're all going to start running at the same time, and they also have a bit of fast memory that they can share, and they can communicate kind of a bit more efficiently with each other than with a thread in a different block. And you can use that for situations where maybe you want a little bit of synchronicity between your threads. So you might try and plan it so that your blocks are a certain size, so that you've got threads that can talk to each other and do all sorts of different things. And so for now, we're just going to use kind of standard rules of thumb that are sensible. And you can look into tuning later. So if you go and look at the number documentation, it suggests that each block should be a round multiple of something called the warp size, which is 32. And again, I don't want to get into a detail of what a warp is. It's to do with how the actual instructions are executed on the hardware. And this was talked about a little bit there was a talk at PyData New York last month by one of my colleagues, Bryce Laubach, where he kind of digs a little bit more into this from the Python side. So if you're interested, go and have a look up Bryce's talk from PyData New York, and that will kind of go into a bit more detail there. So what the documentation suggests is we want to be around multiple of 32, and 128 is kind of a good place to start. So we're just going to decide for the rest of the tutorial, to keep things simple, that each of our blocks is going to consist of 128 threads. We're going to do things in batches of 128, and that just kind of makes our life a little bit easier to think about. Now, this is enough talking about actually what to do. Let's look at some Python code and actually run some things. I also let's just have a look. There's a question in the chat that I'm just going to read out. So correct me if I'm wrong, but you want the kernels to be as long as possible. That way you don't have to often unload back to the GPU memory, which is the bottleneck. You're absolutely right there. We will get to that in like a chapter or so. So I'm glad that you're kind of ahead, but let's keep going with the beginning stuff, and we'll talk about memory management in a little bit. But yeah, absolutely right. So one of the things that I found useful starting to think about this kind of parallel execution in Python is list comprehensions, right? List comprehensions are a nice feature of Python. I use them kind of where it makes sense to. And it's kind of an interesting way to think about things, because it is kind of, it's a very kind of, I don't know how to describe it, like a visually written map operation, right? You can see that I've got, in this first cell here, I've got a range of numbers, just 0 through 9. I've written a little function here, and all this is going to do is just return the number. Right? It's not a particularly exciting function. But if I write a list comprehension, I can call the function for each element in my iterable and get back a list here. So this is just going to pass those numbers straight through. If I call this, I'm just going to get the numbers 0 through 9. Now, range is a generator, so like this is the same as calling like list on a range. But I like this expression because it feels like a parallel operation already, right? I'm going to do an operation to a collection of things in one line in Python. And so let's take this comprehension and we'll start to convert it into a CUDA kernel so that we can run it on the GPU, basically. So that first rule that I said about kernels is that we can't return anything, right? And our function here returns. So let's not do that. instead what we're going to do is we'll start with our data, our input data. We'll also define this empty array called output. And then when we call our function, we're going to append the element to the end of output, basically. So now our foo function, it's going to take in something and it's going to append that onto another variable that exists in the global scope. And so when I call this list comprehension here, we don't actually care about the return value from the comprehension anymore. We just are using it to invoke the function, basically. So if I run this again, we should get the same output, right? We're taking in this range, we're just passing it straight through, but instead of returning, we're popping the item onto output. And then if we have a look at output, it looks as we expect. Now, we have another slight challenge here in that lists in Python are very friendly and let us just randomly add stuff to the end of them, and we can change the length of them, and it's not like a fixed thing. But because we're working with GPUs and slightly lower level code, we can't do that. Basically, we need to decide how much memory do I need for my output ahead of time. I can't just start with this empty list. So we're going to think about that as we run our function. And just to make life a little bit easier, we'll use NumPy for this. Hopefully folks are familiar with NumPy. But we're going to start with an input array and an output array. That is kind of, we know that NumPy is going to allocate a fixed sized array in memory, and we can use that memory space to do stuff. So we'll start out with a NumPy array of our input numbers. We're also going to make a nice NumPy array that's just empty. It's just zeros. It's the same size as our input because we know that the thing we want to do is going to be the same size as our input. And we're going to call our kernel on it. But we're going to do something slightly different here. Because this I that we're passing in, we know is a monotonic number starting from 0 and increasing, right? This is just the numbers 0 through 9. We know that they're unique. Like technically this is a set, right? This is a set of unique numbers and they start from 0 and it's the same shape as our memory. So what we can do is we can just say, well, the first time you get called, I will be 0. So in output at index 0, I'm just going to put the number in, but we could do whatever in here. We could put I times 2 or something in there. Like we're going to do some operation to I, and we're going to put it to some place in memory. And the next time this gets called, I will be 1, and we're going to operate on a different piece of memory. Next time it'll be 2, we'll operate on a different piece of memory. And this is one of the first things we need to think about with the GPU is, okay, I'm running this kernel 1,000 times or whatever. I don't want them to all trample on each other's toes and write to the same memory and read from the same memory. We need some way of having them all do a different thing. And so in this example, where each call to foo is writing to a different bit of memory. So we do our list comprehension again, and we get the same thing. Right? This is just in the NumPy format, but we've updated our output memory. And that's it, basically. Like foo now is a kernel. We can call this a kernel because it doesn't return anything. It updates memory in place and it knows where that memory is. And the last thing we need to do is just decide, well, how many times do we need to run this? At the moment, we're doing it in a list comprehension, but actually we can call this on the GPU. And so let's have a look at what that looks like. Now, I said before, we need to use CUDA to do this, and so we're going to use this nice CUDA submodule from Number, and we're going to create our data array just as we did before, and we're going to create our output array, somewhere to store our values. And we're going to define our foo function. But this time things are going to be slightly different because before, data and output were just these kind of magic global variables floating around that we could operate on from inside our function. But now we're going to be in a situation where data and output are here, they're on my CPU, but I'm going to invoke this function I'm going to call this kernel on my GPU. And so those variables are not accessible. I need to pass those in. So we're going to actually just take these two inputs, our input array and our output array. These are just pointers to those pieces of memory, basically, that we can read from and we can write to. And so you might ask, well, what about I? Where does I go now? I need to know which index I am. And we have this really nice thing in CUDA where you can call this CUDA.grid. And we're going to specify one here because we're talking about kind of one-dimensional grids, and try not to worry about that too much. Like, we'll come on to multi-dimensional grids later because you can do some fun things with them. But what we're going to say here is, okay, we have this grid that we talked about before. This is the number of times I want to call my kernel, and I'm going to ask CUDA, like, within the grid, who am I? Which thread am I? Am I the first time this has been invoked? Am I the 100th time this has been invoked? Like, what is my unique index? And CUDA provides this mechanism so that each time the kernel is called, it can discover and find out, like, who am I, basically? What do I need to do? So we can get I from the grid. We can ask who I am in the grid, and then we can say the index I in the output array, we'll just set it equal to the index I in the input array. And this means that every time we call foo on the GPU, I will be a unique value, because each kernel execution is going to be done on a different thread. And so the thread index is going to be different. And so each time it's going to operate on a different piece of memory. But these will be happening in parallel on the GPU. They're just going to be doing the same thing, just an assignment, but they're going to be doing the same thing in parallel on different bits of memory. Now, the last thing we need to do is kind of like what happened to our list comprehension. But this kind of changes a little bit in the way that number handles things. We're just going to call our function, basically. We have our foo, we're going to give it data and give it output. But we need to tell it, like, how big are you? What shape is foo? What is the grid size? And so the way we configure this is we kind of overloaded the square bracket kind of syntax in Python. So any function that you've decorated with this CUDA.jit, you use square brackets on it to tell it how many times you want it to run. And so we're going to say, I would like one block of 10 threads. This is kind of what we're instructing it here. You say how many blocks you want and how big each block should be. Now we know we only have 10 elements in our array, so we just want this function to run 10 times, and we'll just do one block of 10. We could do 10 blocks of 1 equally here, but we'll do one block of 10, and we'll give it our two things. So when you see this kind of GPU number code, you'll see functions being called this way, where you first have square brackets to tell it what it looks like, how many times to run it, and then you have your normal round brackets to pass in the arguments. But if I then run this cell, I'll get a little bit of warnings here from number saying, the thing that you're doing is very small. You probably shouldn't do this on the GPU. This is a trivial problem, and that's fine, right? We're at 101 stage. We're doing trivial problems intentionally here. It's also complaining about memory copying, which we'll talk about in a little bit. But we got the same result here, right? We've got our array of the numbers 0 through 9, but the only difference here is this piece of code that we've written here in Python was executed on the GPU instead of on the CPU. And I feel like that for me, when I was first learning, was like a big moment. I was like, oh, wow, actually, I've just written some code and I have run it on something that's not my CPU. And that's kind of an exciting thing. And so if there's anything that you take away from this tutorial, is just that you kind of have enough knowledge, enough building blocks to just write code for a slightly different piece of hardware than you're normally used to. Now, as I said, like, it's complaining that this is a small problem. So let's give it a little bit of a bigger problem to think about. This time, let's make a big array with 30 million numbers in it. I will put 30 million random numbers. We'll just use NumPy to generate these on the CPU for now. But if we make this big random array, this is just, each one of these is a number between 0 and 1. We've made 30 million of them. There's allocated, some chunk of memory. If I just do random array dot bytes or size, I can never remember now. Yeah, okay. This is like a 30 megabyte array. It's not the most insane thing in the world, but it's a big array of numbers. And let's do some operation to this. So let's set our output. Let's create our output array as well. We're just going to use the NumPy zeros like operation to say, I've got 30 million numbers in an array. I want an empty array, and I'm going to do something, and I want someone to put my results. So let's make this big empty array to put my results in. And let's write a little kernel to double all of these numbers. I just want to times each of these items in my array by 2. So let's do it in pure Python first, in our kind of parallel way, but let's do it in pure Python and see how long this takes. So I've got my kind of kernel here that I've written. We're going to take in our element, and we're going to update. I'm going to take my index. So who am I within the array? Which element am I operating on? And I'm going to update the output at that index with the input at that index times by 2. And I'll call this in like a list comprehension way, so that we're basically just saying call foo 30 million times, working on each individual thing. And if I run this cell, this is not the fastest piece of code you'll have ever seen, because loops in Python are not necessarily the fastest way to do things. It's kind of part of Python's old reputation of being slow, I think, is that pure Python loops are not fast. So it takes kind of the order of 10 seconds to run this operation. It took 8 seconds to do this. Now let's do the same thing, but on our GPU. So we'll create our output. We've already got our input, right? We defined it up here, our random array. So let's just reset our output back to a bunch of zeros. And now we're going to decide, okay, I need to run this however many times I need to run this. Before I just did it in my head and was like, I need to run it 10 times, so we'll call it 10 times. But now that we've got 30 million elements in our array, we want to think a bit more about how many times do I want to run this? And really, we want to run it 30 million times because we want to do an operation on every element in our array. It's not necessarily true that the length of your data is going to be the size of your computation. If you were trying to do like a rolling window mean or something, you're not going to have as many outputs as inputs. Or if you want to do a mean overall, you're not going to have as many outputs as inputs. But in this case, we're going to go through each element and double it. So we just want to call the function 30 million times. But we decided before, didn't we, that the documentation said our block size should be 128, right? A good standard rule of thumb is we want to do this in batches of 128. So let's set that and say, okay, our number of threads should be 128. And so we just need to know how many blocks we need, right? In order to operate on 30 million elements, how many blocks of 128, how many batches of 128 do we need? And so we'll just use math.ceil and whatever to divide our shape of the array, 30 million, by the number of threads, and then round it up so that we have enough blocks. So we now know, okay, how big is our grid going to be? It's going to be 30 million, and we're going to do, however many batches of 128 it is that we need. Now we can define our kernel. We can do cuda.jit on, we'll call it foo again, but we'll take our input array, our random numbers, and our output array, our empty memory to put the results into. And then each time this is going to get called, we're going to say, which element of the array am I operating on? Where am I in the grid at the moment? Which batch are we in? Which thread am I in? And it tells you. And we're just talking one dimensionally at the moment, so we'll tell it 1. And we're just going to update our output array at that index with our input array times 2. The same as we did in pure Python. We'll do that here. And then when we call this, hopefully this is a little bit clearer because we've given these variable names up here. We're going to call foo with this number of blocks and this number of threads. I'm going to give it some input and output. And now this time when I run this, instead of taking 8 seconds in pure Python, this took 173 milliseconds on the GPU. Okay, so this is much, much, much faster using the GPU to do this operation. Now, those of you who like NumPy and have used NumPy, you may be thinking to yourself, I could just do this in NumPy. Like there's really nice syntax in NumPy for this. I could just do random array times by 2. And if I run this, you'll see, in fact, this is even faster. Right, the NumPy is using all the CPU cores on my machine, and it is just running through and doubling everything in my array. And this is very pleasant syntax. I haven't had to write a kernel or anything. And the reason that this is faster in this situation is this memory overhead that we were talking about before. Somebody asked in the Q&A, like, what about memory? What about, and we've done an operation on a 30 megabyte array, which in the grand scheme of things is not that big. And the operation we've done is just doubling. It's not a very compute intensive operation. And so we're still not using the GPU to its strengths at this point, even though it's like way faster to use the GPU than pure Python. It's still not faster than well-written CPU code. So let's explore a bit about what this memory management is doing and the problems that it's causing us. So when we call our kernel, when we call it up here, you can see that we're passing it random array and output, and these are both NumPy arrays, right? We made these with NumPy. These live on the CPU. These live in main memory, and yet we're calling them in this kernel that's executing on the GPU. And so the reason that this even works in the first place is Number is being clever and helpful, and it's saying, oh, you've given me something that's not on the GPU. I'm going to copy it there for you so that it's there and I can operate on it. And then at the end, I'm going to copy it back again because you're probably going to need it later. And that's what this warning is all about, is saying host array used in CUDA kernel will incur copy overhead. Right, so Number has gone, you're probably going to need this. I'm going to copy it and copy it back again. And that can be expensive when using the GPU, especially if you do too much copying and it's bad. So what we can do instead is we can very intentionally say, I've got my random array. I want to copy it to the GPU. I'm going to do that first. I'm going to create this new variable called GPU random array. And I'm going to create a new variable called GPU output. And I'm going to copy my memory to the GPU. So now that I've run this, if I have a look at this GPU random array, this is now just a pointer to a device array, right? This is some data that's in memory on the GPU. It's not here. I can't see it. It's over there. It's ready and waiting to be operated on by the GPU. And so now if I want to, I can have a look at, well, how fast, if I call my doubling operation on data that's already on the GPU, like how fast is that if I don't have any of this copying overhead? And so if I time this, actually doubling every element in that array is now taking 36 microseconds, right? Which is just tiny. We've gone from 8 seconds down to kind of 170 seconds with bad memory management, or 30 milliseconds on the CPU, but the GPU can actually do this in 30 microseconds, right? It can do this very, very, very quickly because it can leverage all those cores of that GPU. Each core can just be loading a memory, doubling it, putting it back into memory somewhere else. And as long as you don't have to worry about the memory overhead, it's very, very fast. And so there's a huge benefit to putting data on the GPU, doing heavy computation on it, and then copying the result back at the end, and trying not to copy it off and trying not to moving it around. Because if you have to do it every time you call the function, you're just going to be spending so much time in memory management. And this is why GPUs are so popular in things like neural networks or other like computationally heavy operations, where it's like, okay, I'm going to put some data on the GPU and I'm going to do lots of big, heavy matrix operations or whatever. This is kind of where the GPUs really shine. And then at the end, you can say, okay, I want to do copy to host, and it just gives me back a NumPy array back on the CPU. And so just to round off this notebook, if we had a few different kernels that we'd written, maybe we want to break out our whatever we're doing, our algorithm, into a few stages. At the moment, we've only done something that doubles some numbers. But maybe I have like a foo kernel and a bar kernel and a baz kernel, right? Different kernels that are going to do stuff. If I give each one NumPy arrays, Number is going to be kind and copy the array to the GPU, run the kernel, copy the memory back. Is then going to immediately copy that memory back to the GPU, run the kernel, and copy it back again. And then going to move it back to the GPU a last time, run the kernel, and copy it back. And so you've got each of these probably small operations being dwarfed by these large movement operations. So you would write this kind of in this way, where you're going to say, no, I'm going to put my stuff on the GPU. I'm going to do everything to it that I want to do, and then I'm going to copy it back again. And so there's this kind of intentional memory management here. in order to avoid that. So to get the best out of your GPU, you kind of want to put quite a lot of data into the GPU, and you want to do something that's computationally intensive to it. And doubling things is not the best demo of that, but I'm hoping that that was a useful intro to this. Now the next section here is this number lab, and in the interest of time, I think I'm going to kind of just talk through. I'm basically going to skip over this and let you do this in your own time. This is kind of going through reusing everything we've just learned in this first 2.0 chapter. And the goal here is for you to implement the FizzBuzz algorithm, which is commonly used in interviews and HackerRank and whatever. I'm aware that we updated this README, but it didn't quite make it into the material in time, so apologies for that. But the idea of FizzBuzz is I'm going to start with a range of numbers from, in this case, is 1 to 50 million. And I'm going to go through each number. And if the number is divisible by 3, we're going to call it fizz. If it's divisible by 5, we're going to call it buzz. And if it's divisible by both, so 15, we'll call it FizzBuzz. And the goal here is that you just want to do some big parallel operation on your array and decide which numbers are fizz, which numbers are buzz, which numbers are FizzBuzz. And I think it asks you to get like what's the highest instance of fizz. So given that we've got 30 minutes left, I want to get through the next couple of chapters because we talk more about the grid, and I think that's kind of interesting. But I encourage you to come back after and run through these things if you're finding this interesting. So let's move on to chapter 3. We're gonna carry on in number world, and we're going to keep writing some kernels, but we're going to do something actually useful this time and understand a bit more about the data. So we're going to do some image manipulation. So I'm just going to import some libraries to make my life a bit easier working with images. I'm going to specifically use matplotlib. And the only things I want actually from it is matplotlib has got a way of reading in a PNG image as a NumPy array. And then it's got a way of plotting that NumPy array back to a PNG image. And that's great. So we'll use matplotlib for that. Let's load in this image. If we have a look at the type, this is a NumPy array. And if I just if I plot it, we can see the image, right? So we have this, we have the number logo, right, from the open source number project. And this NumPy array is, the however many, 100 and whatever pixels high and 400 and so pixels wide. And then it's 4 channels deep, right? Red, green, blue, transparency, because it's a PNG. So we've got this NumPy array of values that represents this image, and now we can operate on and manipulate this image, and we're going to use the GPU to do it. So let's start by copying the image down onto our GPU. So I've loaded in this PNG into a NumPy array, and I've put it onto the GPU in GPU memory. Now I mentioned to you before that we were working with one-dimensional indexing before, right? And you can do some interesting things with CUDA programming where you can work in more dimensions when it is convenient and useful to the algorithm that you're writing. So let's have a little look at the shape that we have here. We have this image, right? So 116 pixels high by 434 pixels wide by 4 channels deep. If you want to think of it that way, it's kind of a cube of values. And what we want to do in this, is write a kernel that is going to blur our image. We want to take each pixel and average it with the pixels around it to make it look blurry. And so thinking about this from a algorithmic point of view, we want to write a kernel that's going to go through each pixel and do an operation on it, right? It's going to modify that pixel. And so we could think about, well, how many pixels are there, right? There's 116 by 434, and we're going to need to blur each channel as well. So we could times all these numbers together and say, okay, that's how many operations I need to do. That's my grid size. But it might actually be a bit easier for us to kind of stay in this 3-dimensional representation and think, well, actually, I've got this cube, and I kind of just want to roll this little window over the cube, operating on each pixel, and so it should have the same dimensionality as the input data. And really nicely, we can specify this as a tuple. in Python. So we want 128 threads in our batch because the number documentation told us that's a great starting point, 128 threads. And so what we're going to actually do is say the number of threads that I want in my block is 2 threads by 16 threads by 4 threads. I want like this kind of little 3-dimensional representation of the number of threads in my block. So this means that my batches that are going to roll over it are going to be 2 pixels high by 16 pixels wide with all of the color channels kind of covered in one go. And I kind of mentioned like this might be useful if I want to communicate between these layers or something. Maybe I want to communicate about all the color channels or something. I don't know. That could be useful because you can do this communication, and we've like overlapped all the color channels with the size of the block. But I've just arbitrarily chosen these numbers. The only important thing here that I actually cared about was that they covered the full color channel depth and that they all multiplied together to make 128. So I chose 2 and 16 randomly, but this could also be like 8 and 8. 2 and 16 or 4 and 8 or whatever it is that multiplies together to make 128. And so we also then need to work out, well, if I've got these little batches of this shape to roll over my image, how many of those am I going to need? So how many blocks do I need? X and Y and Z dimensions. And so we can just calculate that as well. And it will tell us like we need 58 windows top to bottom, and we need 28 windows left to right. And we only need 1 window on the color channel because we're kind of the full depth of the color channel here. And we can just double check and have a look and say, well, actually, how big is my computation that I've specified here? And this might be a question that came to you in the last chapter. We had 50 million elements or something in our array, and we had these batches of 128, and we worked out how many batches we needed. But are those numbers actually the same? Like, if you times them together, have you got the right number? And actually, in this case, you can see, I think in the previous two, you can see in this case that our grid is slightly bigger than our image, right? We have 116 pixels high. That's fine, that adds up. But we have 448 threads wide. We only have 434 pixels in our image. So actually, there's going to be some threads in the shape of our grid that are off the edge, that are out of bounds of our kernel. And this is kind of interesting that there is no memory safety here, right, in writing these kernels. And so you can just read memory that's out of bounds. And in the last operation, it was letting us do that. We were probably reading the 50 millionth and first element and writing to somewhere else. And the GPU was just modifying that memory. And hopefully nobody else was using that memory at that time. I think if you go really, really out of bounds, number will tell you off if it can catch it at compile time. But it's something that we have to be mindful of, right? We're constructing this grid, but because we're using this nice round number of 128, we might end up with a grid that's slightly larger than we actually need. And so we just need to put a bit of thought into that. Okay, so let's actually write our kernel. There's a question in the Q&A again. Okay, so this question is, apologies if I'm jumping the gun again. Is there a way of using another library like QDF directly inside of Number? You mentioned rolling operations, moving, mean, standard, which is a good example, or am I forced to write these kernels manually? No, so I think that the goal of the tutorial here is that we're talking about a lot of low-level CUDA stuff to help give you an intuitive understanding of what these devices are doing. But ideally, if you're working up in Pandas level and you want to do a moving mean, you can just use the Pandas API with the QDF plugin, and it will do a moving mean. And you don't need to think about kernels or blocks or threads or anything like that. But under the hood, this is all being done for you. It's calculating all of these things for you, and it's operating in this way. And so hopefully it's maybe kind of clearer that a moving mean is quite a parallelizable operation, right? You can just read all of these windows in one go and calculate over that operation. Like if you want to do like a rolling window, if you're doing something where you're trying to follow the mean along, then that's going to be like a sequential operation. And so there's cases where this is going to be good, and there's cases where this is going to be bad, and you've got this parallel hardware that's good for some use cases and worse for others. And I think Katrina in the chat like linked another nice documentation page that talks about when it's good to use the CPU and when it's good to use the GPU. And ideally, you can just use them both to their strengths and get the fastest operation you can. Okay, let's talk about our blur kernel then. So let's actually write this code. We're going to define here blur, and we're going to take in our image. So this is our NumPy array of our image, or actually this is now our device array, right? Our GPU device array of our image, and we also have like an empty output array ready for the output to go into. And what we're going to do is we're going to get our indexes again, but we're going to call CUDA.grid3. And this is because we're specifying our shape and size in 3 dimensions. We want to ask where we are in the grid in 3 dimensions. So we're effectively saying, like, what is my X, Y, and color channel position within the grid? Am I the first thread that's running? Am I the 1000th thread that's running? And if I am the 1000th thread, like, what does that mean my X, Y, C position is? Can you tell me? And CUDA will work this out for you. You don't have to worry about like wrapping and unwrapping these higher dimensional data structures. So then once we found out where I am, X, Y, and C, I've got a little guard in here to just say, am I actually inside the image, right? I know the length of the image and the height and the color channels. Like, is my coordinate actually within bounds? And if I am within bounds, then I'm going to do something. If I'm not within bounds, it's just a no-op, and this thread is just going to not do anything. So we are kind of asking for more threads than we need, but only a little bit, because we need round numbers. And then the last thing we're going to do here is actually do our operation. So we're going to set a value in our output array, and we're going to set it to, if we have a look here, this is the pixel that we're reading in from. And we want to take the mean of kind of all the pixels around it, right? All its neighboring pixels. So if you've got one pixel in the middle, you've got kind of 3 above and 3 below and 2 either side. You've got this little window of 9 pixels. We want to take the mean of that and put that into the output array. And I tried to lay this code out so it's almost like visually you can see, like, we're reading that pixel, and the one above it, and then the one in the top right corner, and then the one to the left of it, the pixel itself, and the one to the right of it, and whatever. So we're going to read in each of these pieces of memory, and we're going to divide by 9. Now, I hope this also kind of shows that, we can read any memory that we want from this array. Like, for actually implementing this operation, we want to read the pixels around. But each of these values is going to be read more than once, because if I'm at 1010 or something, I'm going to read that pixel, and I'm going to read the pixels around it, and then when I'm the next pixel over, I'm going to read those. They're like overlapping windows. So you're reading from these various bits of memory, but that's totally fine, because as many threads as you like can read from these bits of memory. It's only when we're writing that we need to think about, like, each kernel needs to write to a unique place, otherwise they're going to overwrite each other's values. So we're just setting this XYZ position despite reading a bunch of other positions. Let's just define this. Now, when I run the kernel, the last thing I want to do is we're doing a blur, and we're taking the average of these pixels, but it's not actually, when you look at it, or when I was writing this and I looked at it, it's not a very blurry blur. It's just like a very subtle blur. So actually, what I probably want to do is blur it a few times. And so this is a really nice example of reusing memory on the GPU and also just avoiding copying things around. Like, I have my one kernel that is blurred the image, but actually maybe I want to blur 5 times or 10 times or 100 times to get the kind of depth of blur that I need. And we don't want to be copying memory back and forth from the GPU to the CPU in there. So what I'm going to do a normal Python for loop. and I'm going to call blur my image, right? I'm going to take my input image and my output image, and I'm going to blur it. So I'm going to start with this array of the image, and I'm going to blur into this array. So I now have kind of the starting position and the finishing position of this call. And then all I'm going to do is I'm going to flip the pointers around. So I'm just going to say input becomes output and output becomes input. So I still have these two arrays in memory on the GPU, but I'll change their names so that next time I call blur, I'm going to go from this first level of blur, and I'm going to blur back into this first array, right? And I'm going to flip the pointers, and I'm going to blur back, and I'm going to just keep blurring from left to right between the two chunks of memory. So I'm not having to allocate new memory each time. I'm not having to copy any memory anywhere. I'm just reusing these chunks of memory space just by flipping the pointers around. So if I do this 5 times, and then we look at the image, so we're gonna intentionally copy our image back, and then we're gonna do show. We get our kind of blurry picture here, and I could call this again and blur it like another 5 levels, and it gets maybe even blurrier. Now there's a question that's just come up in the chat, which you might see some funny artifacts in this image, because there's kind of an intentional bug that I left in here, because I like to talk about this. Is that the question in the chat was, since we're doing x minus 1 and x plus 1, shouldn't we check those bounds as well? And yeah, absolutely. Like, we're doing this little guard to say, like, have I gone off the edge of the image? But if I'm in the very top corner, my first starting point, or the very bottom corner, wherever 0, 0, 0 is, if I read -1 to the left and I read -1 below 0, 0, 0, I'm reading off the bottom of the image. Kind of here, this pixel is out of bounds, and you can kind of actually see that here. This kind of gray blurriness coming up from the bottom and down from the top is we're reading values that are out of bounds. We don't know what is in that memory. It might be some other data structure. It might be some of the output memory. I don't know. It might just be other random bits of memory. It might just be a completely unallocated RAM. And when you boot up a machine for the first time, all the bits in the RAM are just kind of random values. It's just however the electricity lands, they stay in that state. And so you kind of RAM just starts up with a random configuration anyway. And as part of the boot process, like, weird stuff might end up in it. And so we're just reading random stuff off the bottom and off the top. And so we get these kind of gray lines. And so we need to be conscious of where we're reading from, and we probably need some more guards in here to make sure that we're not doing that. But I like to leave that in as a bit of a demonstration of that. So thank you for the question. So that question is, okay, so to follow up, it's not so bad because we're reading and not writing to those. I mean, we could absolutely write to those as well. That's probably not a good thing to do, because you don't know whose memory that is. If it's unallocated, then fine, you're probably just writing nonsense into empty space. But if it is some other variable, you're going to overwrite it, and that's bad. So you want to be guarding for these things. And if you were writing normal C code for the CPU or something, you would get a seg fault at this point, right? You're not meant to read this. You would get like an error. But in GPU world, you're kind of that little bit closer to the hardware, and so you do have to be mindful, or at least when you're writing low level stuff. When you're up in QDF world doing pandas type things or whatever, all of this is taken care of for you. Again, my hope is that this tutorial is kind of giving you some intuition, and also maybe hopefully you're thinking, I hope I don't actually have to write this stuff day to day. I'm finding it interesting learning about it, but I just want to use the high level APIs. And that's great, because we're putting a lot of effort into the high level APIs. They get covered in the later chapters. Okay, we have 15 minutes left. I did want to try and get to the end of chapter 3. Now there's another lab here, and I think because this is a condensed one, I'm gonna jump over the lab. But I'm gonna talk through the solution to this one, because it has some interesting things in it to do with dimensionality that I just want to kind of cover and talk about here, because everything we've done so far, we've had some input data and some output data and a grid, a CUDA grid computation, and they've all been the same size in theory. Like we've wanted to do the same number of operations. But this is the kind of the first example we have where we don't want to do that. So let's run through this kind of solution to this lab and talk about that. And then we'll do some closing things and have a bit of a chat about other tools and stuff that's available. So same dependencies as before. Let's get matplotlib. Let's import. Let's load up that number logo again because we're going to do some more image manipulation. And let's copy that onto the GPU. So we have our image on the GPU. We have our output array on the GPU. The other thing that you might find interesting to just point out here is we started very simply with an output array that was empty, right? And we were like, oh, we actually need to allocate some memory of a certain size, so we make some zeros. But it's a little bit inefficient to make an array on the CPU that's full of zeros. Right? We're doing np.zeros like, and then doing CUDA.toDevice of an empty array. So we're spending some time making loads of zeros, and then we're copying all of those zeros somewhere else. That's not the most efficient thing we could do. We can do CUDA. I think we could do like CUDA zero array. I can't remember now. Let's have a quick look. There's a few calls in here. I can't remember off the top of my head, but you can specify, make me an array of zeros directly on the GPU, and you can also just say, make me an empty array of this shape on the GPU. Don't go through the effort of zeroing everything out because I'm just going to write to it immediately in a second. So it's there are more efficient ways of doing things, but I just thought that'd be interesting. So what we're going to do to this image this time, instead of blurring it, what we want to do is kind of make it black and white. We want to grayscale the image. And the way that we do that is we just look at the red, green, and blue channels for a pixel, and we take the average. Right? When red, green, and blue are the same value, it's gray. So the way that we're going to do this is we want to operate over our image, but last time we did it in 3 dimensions, right? We blurred the blue, we blurred the green, we blurred the red, and we blurred the transparency, which I don't know, maybe we didn't need to quite go that intense with it. But what we want to do this time actually is we want to window over our image and operate on each pixel, but we want to work on red, green, and blue in one go, right? We want to read from red, green, and blue, and we also want to write to red, green, and blue. So we just want one thread operating on each pixel. So instead of this being a 3-dimensional calculation, this is just a 2-dimensional calculation. Even though in theory our array is 3-dimensional, we're doing a 2-dimensional calculation. So again, we want 128 threads because that's just our nice rule of thumb for the tutorial. So this time we're just going to do blocks of 16 by 16. Just again, these are arbitrary numbers. They multiply together to 128. Some algorithms you might benefit from a different shape here, but we're just going to go for little squares because why not? And we're going to work out, well, to window over my image, how many of these little squares do I need? I'm going to run that. And now let's have a look at our kernel. So this is our black and white kernel. And we're going to ask it CUDA.grid2, right? So we're talking in a 2-dimensional space. Where am I in the 2-dimensional space? Which is effectively saying, what is my XY position in the image? And we've got our guard here as well, because our grid is slightly larger than our image. We shouldn't be operating out of bounds. So let's put our guard in. And that's it, actually. We're not reading from any other memory other than what we're guarding for here. So that's absolutely fine. We're just, we don't have any out of bounds issues in this one. And so what we're going to do is we're going to read the red channel. We're going to read the green channel, and we're going to read the blue channel. We'll add all of those together, and then we will divide that by 3. So we're basically just calculating the average value for red, green, and blue, and then we're updating the output array in each of those channels. So for our pixel position, red channel will be the average, green channel will be the average, blue channel will be the average. And we're also just going to pass that alpha right through because it doesn't we're doing black and white. It doesn't really make sense to include transparency in this calculation. So we're just going to say if there was transparency on this pixel before, there will be transparency on this pixel afterwards. We'll just pass it through. And so that's our kernel here. And so if we call this, we say I want this number of blocks made up of this number of threads. That will cover my whole image. And I'm going to pass input and output. And then if we plot it, we can see we get a gray version of our data structure, which is great. But you could imagine like a bunch of different shapes and sizes that you might want to have for these computations. And you might not want the input and the output to be the same size. If you think about something like, okay, we're in pandas, we've loaded QDF pandas, we have a data set, we have a column, and our column is temperature for a weather station or something, and we call column.mean. The input is however long that column was, right? How many values we have in the weather stations, and our output is an integer or a float, right? It's a single number of what is the mean temperature. And so when you think about parallelizing that on the GPU, what you're probably actually going to do is you're going to break up your column. Say it's got like 10 million elements in or something. You might break that up into chunks and calculate a mean, like a kind of like you're doing almost like a reduce operation here, but you can do it in like a tree reduce where you say, okay, I'm going to take loads of chunks and I'll calculate the mean of those, and I'll have this kind of intermediate stage where I have maybe 1,000 intermediate means, and then I will add all of those together and calculate the final mean. Maybe you have a few layers and it looks a bit like a network that's like a tree getting smaller. And so the kernels that have been written for these libraries by our team in Rapids will be doing these things where I'm going to read in my input data, I'm going to call the kernel however many times I need to take the mean into this intermediate level, and then I'm going to call the kernel again to take the mean down to the next intermediate level until I've already gone all the way down to my final mean. But I've managed to parallelize up that mean operation and leverage all the cores. And so you don't have to have this mapping between the two. You just need to think about, well, what does my input data look like? What does my output data look like? And what does the computation look like? Is it this, these three things can have different shapes. And this example kind of showed this three-dimensional image had a two-dimensional computation to calculate that. Perfect. Okay, so for the last 5 minutes, let's just talk about a few kind of extra bits and pieces to dig into. So let's talk a little bit about the rest of the tutorial. As I said, you'll have these instances. Please go ahead and run through these. You can also run through these on Google Colab if you like. The next chapter, we talk about how to see what the GPU is doing, understanding how busy it is and how much memory is being used, and the kind of stuff you'd use Task Manager or HTOP or something for. And we have a nice plugin for Jupyter. Unfortunately, it's not installed in this environment, but if you install this Jupyter Lab MV Dashboard Jupyter plugin, you get these nice graphs showing you how busy, what's the utilization of the GPU and how much memory you're using and various things. And this notebook talks through a bit about how we get these values out of the GPU and asking it various questions about itself, which is interesting. Something else I want to highlight is we talked about one type of array, right, on the GPU. We had a NumPy array, and then we used number to copy it onto the GPU. And we ended up with a number device array. But there's like a load of different nice GPU accelerated Python libraries for working with arrays. And a lot of effort has gone in to make all of these things as compatible as possible. So you can actually, if you created an array with number, you can use that array in PyTorch, or you can use that array in CuPy, or you can use that array, and you don't have to copy it back to the CPU and copy it back again in a different library, and you don't have to even copy it on the GPU from one type to another. You can just wrap that array in another little bit of metadata, I guess, and pass between. And so there's a notebook here showing going from CuPy to number to PyTorch and back again, and we can just copy memory around. And this is great if you want to do some machine learning and you're using PyTorch, but you want to do your preparation and cleaning in a different library like QDF or CuPy or something, then you can just work on the same chunk of memory in the GPU. You don't have to pay that penalty and all that kind of stuff. And then the last couple of chapters here kind of dig into CuPy, which is our NumPy-like library, QDF, which is our pandas-like library, and QML, which is our scikit-learn-like library for doing the kind of things you would do for all of those. There's also a last notebook here on Dask, which is kind of talking about either doing multi-GPU operations or for doing operations that are larger than the memory of your GPU. So if you don't know Dask is great at chunking up like big NumPy operations or big pandas operations and distributing them and swapping chunks of memory in and out. And because all the Rapids libraries follow the same APIs as these other libraries, Dask works nicely with CuPy and QDF and other things. The other thing I want to just highlight, which also is just making its way into this tutorial, but didn't get there in time for this session, is if you go to rapids.ai, which is our just our main website, there's a couple of things linked here. One of those is that we now have polars support. So if if you've heard me talking a lot about pandas and you think, well, everybody's getting keen on polars these days, we have GPU support in polars as well now. And Richie, the creator of polars, gave a great talk at PyData New York about that code there. And then also the other thing to show you is if you go to the Pandas Accelerator mode for QDF page, have a look at this. This is basically what I was showing you before about how you can keep using pandas but get the GPU acceleration. There's a notebook linked here that runs on Colab, which is kind of a 10 minutes to QDF.pandas. And that's another great notebook that kind of walks you through doing pandas operations and shows you the performance differences between pandas with a GPU and pandas without. So yeah, that's kind of everything I wanted to go through. Please do run through these notebooks. If you have any questions or you want any further support, go to the Rapids website. Scroll to the bottom. Is it the bottom? Somewhere on here, it says about our Slack. We have a Slack, and if you have any questions, go and reach out to us on Slack. I can't remember. There's a link on here for sure, somewhere. Anyway, I won't labor the time finding that. But if you need help, go and find us on our Slack, ask questions. We're always around. We're always happy to chat to people. But yeah, that's kind of us on time. If you have any more questions, please do put them in the chat. I'm more than happy to answer, but thank you for all sticking around to the end, and I hope this has been useful.
All right. Well, a big thank you to you both for this presentation. I thought it was very interesting. I hope that the audience enjoyed. I saw a lot of participation in the chat, which was really nice. We do have about 2 minutes if there are any final questions. Otherwise, we can go ahead and wrap this session up. I'll wait for just a minute and see.
Sure.
All right, I'm gonna say we're good to go. But
Perfect.
for all the attendees, if you have any additional questions, want to continue the conversation, like Jacob mentioned, there is the Slack channel you can join. We also, on PyData side, we have our PyData Discord where you can chat with your fellow attendees, and we also have the lounge feature on AirMeet. But a big thank you to both Jacob and Katrina for hosting today, and this concludes this session.